In Chapter 4, we're going to learn about cyclic groups. Let's look at the definition. A group G that can be written as G equals that bracket A for some A and G is called cyclic. In this case, A is called a generator of G, and we call G the cyclic subgroup generated by A. So now we have a name for this symbol with those brackets. We're going to call that the cyclic group generated by A. Easiest way to learn about this, let's look at some examples. So in example 1, we're going to investigate 3 different groups and see if any of them are cyclic. Let's start with U5. So that is a group of units, mod 5. The operation is multiplication, mod 5. Okay, so this is multiplication, mod 5. And what's in here are all the elements that are relatively prime with 5. So 1, 2, 3, and 4. Let's start and see what happens when we take those elements and just look at powers of them. Because if you remember, we have encountered this symbol before, and it was a set of a to the 0, a to the 1, a squared, dot, 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 and then we also had the negative powers, a to the minus 1, a to the minus 2, dot, dot, dot. So this is what this notation meant for us before. All right, taking 1 to powers is not particularly interesting. 1 is the identity element in this group U5, and if you take the identity and just multiply it by itself, you just get the identity back. So we don't get much there. But 2, let's look at 2. What happens when we take 2 to powers? Well, 2 to the 1, that is just 2. 2 squared, that is 4. Mod 5 is still 4. 2 cubed, that is 8. Mod 5 is 3. So 2 cubed is 3. And 2 to the 0 is the identity, 1. We can keep going and look at, I don't know why I looked at 2 to the 0 actually. I didn't really want to do that. Let me get that out of the way. After 2 cubed, we want to look at 2 to the 4th. 2 to the 4th, that is 16. Mod 5, that is 1. And we've cycled around. So we had 2, 4, 3, 1. 2 to the 5th would be the same as 2 to the 1. So that is just 2 again. And so on. So we are really cycling through these numbers. And there is a nice way to show this with a little diagram. This cycle structure of our group. We can just make a little circle, and we have 2 to the 1 somewhere, and then we have 2 squared, and then we have 2 cubed, and then we have 2 to the 4th, which happens to be 1, which also happens to be 2 to the 0. So 2 to the 0 is also the same as 2 to the 4th. And so we are starting to go around in a circle. So after 2 to the 4th, we'd get 2 to the 5th, but that is the same as 2 to the 1st power. And then 2 to the 6th is the same as 2 squared. 2 cubed is the same as 2 to the 7th, and we just cycle around and around and around. So we just have these 4 different elements that we keep going around and around, and so this is why we call this a cyclic group, because of this behavior. Now, we could also go in the other direction and pick up all the inverses. So we could go around the other way and starting at 2 to the 0, if we go around the other way, I would get to 2 to the minus 1. And then if I keep going, I'd get 2 to the minus 2. And if I kept going, I'd get 2 to the minus 3. And so on. Let's do one more. I'd also get 2 to the minus 4. And you can convince yourself that these really are the inverses of 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and so on. Now, we already said what all of those numbers are. 2 to the 0, that is our identity, element 1. 2 to the 1/5 or minus third, that is really just 2. 2 squared, that was 4. And 2 cubed, that was 3. So my diagram is getting a little bit busy, but in this cycle, you're really seeing a lot of what is going on in this group. And we picked up every group element just by taking higher and higher powers of 2. We cycled through every single element in U5, and so we are saying that U5 is cyclic because U5 is equal to the group generated by 2. It picks up everything. We get our identity, we get 2, we get 3, we get 4. Everything that's in U5. So here's an example of a cyclic group. And so we've answered our question. U5, part A of this problem, U5 is a cyclic group. Let's look at part B. Let's look at part B. What about U8? So U8 is all the integers that are relatively prime with 8, multiplication mod 8. So that is 1, 3, 5, and 7. Is that cyclic? Well, let's see. Let's see what we get when we look at each element right here, what we can generate. Well, 1, I already mentioned it, but I'm going to write it down. It doesn't give you much, it just gives you 1. What do you get when you take powers of 3? If you take powers of 3, well, you get 3 to the 0. That is the identity, so we do have the identity. And then 3 to the 1, that is 3. Okay, and then 3 squared, that is 9. Mod 8 is 1 again. So I don't get anything new. I just have a 1 and 3. What about taking powers of 5? I get 1 for free, and then I get 5, and then 5 squared, that is 25. Mod 8 is 1 again. So I also only have 1 and 5. Okay, let's see. What do I get when I look at powers of 7? I get 1, I get 7. 7 squared, that is 49. And 49 is also 1 mod 8. So, okay, I went through all my elements and none of the sets that I generated by taking powers gave me the entire group. So that means U8 is not cyclic, because no element of U8 generates all of U8. Okay. Running a little out of space, but we can look at part C. Let's look at part C. Z, what about Z? Is Z cyclic or not? Actually, we already talked about that. It is cyclic. And what are generators? What are generators of the integers? Z is under addition, so it's our group under addition. So what number can you add to get all other integers? 1 works. And note 1 is not the identity. The identity here would be 0, but in this group. 0 is the identity for the integers under addition. But the number 1, the element 1, you can add repeatedly, or you can look at inverses and you get all the other integers. There is one other generator, and that would be, oops, wrong notation. I want my bracket. That is -1. That would also work. So we have 2 generators for the integers right here. So just to summarize, U5 was cyclic, U8 was not cyclic, Z is cyclic. And you should do example 2 and investigate Z4. So Z4 is 0, 1, 2, 3. The operation is addition mod 4. And see if you can figure out what is going on in Z4. Is it cyclic? Well, it says that you are supposed to show that it is cyclic. But you figure out what are the generators.